Fantastic with Professor Michio Kaku.
This is Science Fantastic with Professor Michio Kaku. On Science Fantastic, we profile the amazing, jaw-dropping scientific discoveries which are revolutionizing our world and touching our lives. And in this hour, once again, we're going to throw the lines open because this hour is your hour. Okay, well, let's move right along to the first listener phone call.
Hi, my name's Ken from Ormond Beach, Florida, and I was curious if for some man-made reason or unnatural reason the ozone were to disappear, what would happen to the gases on the Earth? Would they just dissipate into space, or would microgravity or some other force keep them attached to the Earth? Thank you.
Well, the short answer is none of the above, but let me tell you what happens. First of all, ozone depletion is separate from the greenhouse effect, though there is a relationship between the two that's very slight. First of all, ozone is a protective layer around the planet Earth that protects us from the harmful ultraviolet radiation from the sun. However, chlorofluorocarbons, especially caused by refrigerants and other chemicals, man-made chemicals, go into the atmosphere and disrupt the ozone layer, which is made out of oxygen. O3- is the scientific term for ozone. And if the ozone layer were to ever completely disintegrate, this very thin layer that protects the Earth would allow tremendous amounts of harmful X-rays and ultraviolet radiation to hit the Earth. Therefore, any animal with eyes would be blinded, crops would wither, eventually mammals would have a hard time living in a world where there's so much ultraviolet radiation coming from the sun, and it would imperil life on the planet Earth itself. And so we have what are called the Montreal Protocols. The nations of the Earth got together, and they all decided this is something that they could really rein in. Chlorofluorocarbons for refrigerants was not that big an industry yet, so why not phase them out? There are other ways to cool down your refrigerator without using the chlorofluorocarbons. And so some people say that was a success story where the nations of the Earth finally did something constructive, and sure enough, when you look at ozone depletion by satellites used to show that there was a gigantic ozone hole over the North Pole and especially the South Pole. So we knew that the ozone layer was breaking up. We had graphic proof of this with holes breaking up over the North Pole and the South Pole, holes on the ozone layer. However, now the holes are slowing down, and so many people think this is a success story. Now, of course, the greenhouse effect is a totally different question. Greenhouse gases are interlinked with economic activity. Basically, the burning of fossil fuels creates energy, electricity, by which we energize our society. And so it's much more controversial. However, ozone depletion was not so controversial, and fairly easily the nations of the Earth realized that, yes, we can use other chemicals to cool down the refrigerators without chlorofluorocarbons, and bingo, it is now seen as a success story. So the main danger with the loss of an ozone layer, hypothetically, would be tremendous amounts of harmful ultraviolet radiation, which would cause cancer, which would basically blind animals with eyes, and would eventually ruin crops. So there would be crop collapse if the ozone layer were to ever completely disintegrate. Okay, well, let's move right along and take the next listener phone call.
Yes, Professor Kaku. I listen to 106.5 here in Arkansas, and my question is, I have a hard time understanding that space is infinite. It just seems like in my mind that it has to have a starting point, but an ending point. So somehow, could you explain that to me where somehow I could comprehend or understand that? Thank you very much.
Well, you ask one of the most ancient philosophical questions that even the Greeks asked themselves 2,000 years ago. And if you want to embarrass a physicist, and see their face turn red, ask them that question. Is there a limit to space? And what happened before the beginning of time? Did time and space start all by themselves, or were they always here? It turns out that we really don't know the answer. However, we have a framework by which we can ask that question, and that framework, of course, is Einstein's theory of general relativity. Now, the latest version of Einstein's theory says that the universe is a bubble of some sort. We live on the skin of the bubble, and the bubble is expanding. That's called the Big Bang Theory, and it agrees with all the data points that we've measured the universe with. But then the question, of course, is, well, is there an end point to the bubble? Let's say you're moving in a certain direction. Will you ever hit a wall, a brick wall that says the end of the universe? And if there is a brick wall out there, then what happens on the other side of the brick wall? Well, if the universe is a round sphere, and of course that's not for sure, then you would simply come back and meet your original point by going all the way around a circle. So an ordinary sphere, like a bubble, is finite in 3 dimensions. After all, it's nothing but a bubble, duh. However, in 2 dimensions, it's infinite, because you go around and around and around and around and never come to the end. So if the universe is a spherical bubble, and that's not for sure yet, you walk in a straight line. Ultimately, you come back to the starting point, and you see all the garbage that you left, the empty Coke bottles that you left billions of years ago when you set out on this journey to go around, completely around the universe. So if the universe is really 4-dimensional, as Einstein thought, then the universe would be finite in 4 dimensions, but infinite in 3 dimensions. So just like an ant would go spinning around a globe an infinite number of times and never reach the end of the globe, we, like ants, moving in the 3rd dimension, would go in one direction and never hit the end. But we will eventually hit our starting point. Now, is that really the way the universe is? We're not sure. Sorry about that. It could be that the universe is actually infinite. Now, last year we had on our airwaves Dr. Alan Guth of MIT, who proposed the inflationary theory, a theory which says that a tiny little infinitesimal dot of space-time blew up to create the entire universe as we know it. If that theory is correct, then maybe space is really infinite, and Big Bangs happen all the time. So if the Big Bang happened in this sector of the universe, if you move in a straight line far enough, then you would see yet another Big Bang take place. So what's the final answer to your question? Sorry about that. The answer is we don't know for sure. The leading theory is inflation, but then the question is, where does inflation come from? Well, we're not sure about that one either, but the leading theory as to the origin of inflation is something called string theory, which is what I do for a living. And, however, I should point out that string theory is not totally verified. But string theory says that the universe is an 11-dimensional sphere. So that if you were to walk in a straight line in 11 dimensions, perhaps you would come back and meet yourself and see all the Coke bottles that you left a few billion years earlier.
You're listening to Science Fantastic with Professor Michio Kaku. Professor Michio Kaku.
Welcome back to Science Fantastic with Professor Michio Kaku. Once again, on Science Fantastic, we're going to throw the lines open, so this hour is your hour. This is the time when you can get to the phones and call 866-323-2129 and have your thoughts heard on national radio. That's right. Give us a call at 866-323-2129 and you can get on Science Fantastic. Well, it's open mic on Science Fantastic, so let's move on to the next listener phone call.
John, KFQD, Alaska. Doctor, I was wondering, with the recent seismic events and radiation leaks in Japan, is there any chance that these may reawaken Godzilla as well as Rodan and Mothra? And is there also a chance that they will not only destroy Tokyo, but the rest of the world as well? And how can we vanquish these creatures from the face of the earth forever? Thank you. Bye.
Okay, well, you asked some revealing questions about politics and science and the Cold War. First of all, right after the end of World War II, the United States was testing nuclear weapons, and in one test, tremendous amount of fallout came raining down back on the planet Earth, and there was a small fishing boat that was accidentally caught in this downpouring of very radioactive fallout from the test. The little boat, unfortunately, was a fishing boat called Lucky Dragon. It was not lucky, of course, because when the ship docked, all of a sudden the crew members came down with a sickness, radiation sickness from the hydrogen bomb tests that the United States was conducting. That created a sensation in Japan. Not only were they reverberating from, of course, the effects of Hiroshima and Nagasaki, and now we had the sad story of the Lucky Dragon, which inadvertently sailed into a rain of fallout, causing radiation burns over the bodies of these fishermen. So, some enterprising filmmakers said, let us make this into a morality tale. That perhaps the nuclear age is opening up new demons and monsters that we are totally unaware of, that can catch us off guard. Well, it was known even before the bombing of Hiroshima and Nagasaki that radiation can cause mutations. If you get fruit flies, for example, hit them with X-rays, look at the next generation, sure enough, you can see mutated fruit flies in the next generation. So it was already known from the work of Dr. Mueller and others that intense radiation will cause radioactive damage to our genetic makeup, leading to mutations. So, said the enterprising filmmakers, let's take Lucky Dragon and make it into a real dragon, a gigantic dragon. So they said, let's call it Godzilla. Okay, so Godzilla was basically Lucky Dragon reincarnated to wreak revenge on us poor Earthlings for opening up the secret of the atom. Now, I mentioned this story because a lot of you millennials out there have probably never seen a Godzilla or a Rodan movie. However, they're on the Internet. You simply Google it, and you can find versions of Godzilla, very crude by our standards, even though it's been, of course, redone several times with modern special effects. But basically, it's a morality tale, like Frankenstein. Sometimes the creations that you make in the laboratory come back and bite you, and that's what it's all about. Now, the caller also mentioned the earthquakes, so let me say a few things about that. Japan was hit twice recently, with earthquakes, and then Ecuador. Ecuador was also hit with an earthquake, and then people thought, is there a connection? We see Japan hit with 2 earthquakes recently, and then Ecuador very soon after that, just a few days later, being hit with earthquakes. Is there a relationship? Well, the short answer is no. However, we should point out that Ecuador and Japan and the west coast of the United States all lie on the ring of fire. Take the globe of the Earth and draw a ring around the Pacific Ocean, starting in Chile, going up to Baja, Mexico, to California, up to Alaska, up to Russia, Japan, down to the Philippines. And that ring is where 90%, I repeat, 90% of large earthquakes take place in that ring of fire. And believe it or not, we could experience new earthquakes in the United States as a consequence of this. Just a few weeks ago, it was announced by a scientist that in some sense, the San Andreas Fault is overdue for an earthquake. Let me be more precise about this. The last major earthquake in California was, the 1906 earthquake, which hit San Francisco, but also the 1857 earthquake, which hit L.A. Now, the cycle time for earthquakes, and then, of course, this is very approximate. It's not exact at all. But the rough cycle time for earthquakes along the San Andreas Fault in California is roughly 150 years. If that's true, then the earthquake of the 1850s that hit Los Angeles means that we're probably overdue for an earthquake again. Again, we're not sure, but on the radio, I've interviewed a seismologist who said that the most likely place for the next break in the San Andreas Fault is northern Los Angeles. We don't know for sure. This could be completely wrong, but the computer programs and the analysis done so far seem to indicate that northern L.A. is the site of the next earthquake, which lies around the Pacific Ring of Fire. I should also point out that Seattle and Washington, Oregon State, they're not immune to this either. We have the Cascadia Fault, one of the biggest faults off the coast of the United States. It could sustain a 9.0 earthquake, which could, of course, wipe out huge chunks of Oregon and Washington State.
Don't feel bad. I didn't understand theoretical and dimensional metaphysics the first time either. But if you call and ask, Professor Kaku will get you there. You're listening to Science Fantastic. This is Science Fantastic.
Welcome back to Science Fantastic with Professor Michio Kaku. This hour is your hour. This is the time when you can shine. This is the time when you can get to the phones and call 866-323-2129. And if you call, all you have to do is leave your name, call letters of the radio station, and the city you're calling from. And perhaps your thoughts will be heard on over 100 radio stations that carry Science Fantastic. So, once again, sometimes some of the dumbest, simplest questions are the most revealing of all. It was when Isaac Newton was practically a teenager, he asked himself a question which would change all of modern science. And that question was, why do apples fall? If an apple can fall, does the moon also fall? And when Isaac Newton answered that question, when he was 23 years old, it changed the course of modern history. Because all of a sudden we had a mechanics by which we could explain the properties of machines, the planets, the comets. Newtonian mechanics would then set the agenda for the next 300 years. The Industrial Revolution owes its origin to a simple question. If an apple falls, does the moon also fall? And the answer to that question is yes, the moon also falls. Okay, once again, you are listening to Science Fantastic with Professor Michio Kaku. Give us a call. The hotline number is 866-323-2129. So moving right along, let's take the next listener phone call.
Yes, my name is Vincent, and I was wondering, which water is healthier for you, rainwater or well water from the ground? I listened to 1470 WFTL. Flint, Michigan. I want to know which water is healthier for you, rainwater to drink or groundwater to drink from your well. Thanks, bye.
Okay, well, you ask a very interesting and relevant question these days, and the short answer is, well, it depends. In the main, if you were to make a very quick decision, you would have to conclude that rainwater is perhaps healthier than well water, but again, the answer depends. First of all, rainwater may not be quite as pure as you think. First of all, rainwater, of course, comes from the evaporation of water on the earth, and that evaporation process is a filtering process. So water in a relatively pure form begins to evaporate from even polluted water, leaving the pollutants behind. However, once we have water vapor in the air condensing to form rainwater, there are many things which are water soluble which are not so good for you. For example, mercury. Mercury, in the main, comes from man-made sources of pollution. And when the mercury and other chemicals wash into the water through rainwater, it creates acid rain. So acid rain, as well as elevated levels of mercury, are both consequences of chemicals that are washed into rainwater as they come down. However, well water has yet a whole nother set of questions because, of course, well water, well, it all depends on what's down there in terms of previous pollution, in terms of whether or not the ground table has been polluted, and so on and so forth. Now, I should point out that when water goes through the ground, it is filtered. Just like when water evaporates and goes into the sky, it's filtered. Water also is filtered as it goes down toward the earth. So there is a filtering process. However, let's be fair about this. There are also pollutants in the soil itself that can get in the way. For example, I live in Manhattan, but outside Manhattan there's a city called Montclair, New Jersey, a very nice, comfortable, middle-class town. But decades ago, U.S. Radium was there. It built, radium watches for the military. And back then, there were radium workers that would lick their brushes and paint the dials of military watches with radium. Well, it's a very sad story. First of all, many of these women came down with horrible radiation poisoning, leukemia, and other kinds of problems because radium is not good for you. It's highly radioactive, and they were licking the brushes as they painted the watch dials. Second of all, what did U.S. Radium do with all this excess radium? A lot of it was just dumped into the environment. And decades later, when people began to build housing tracts on these things, what did they find? Oops! They found radium left over from U.S. Radium. Also, take a look at Grand Junction, Colorado, a very nice suburban housing area, but underneath Grand Junction, Colorado are the waste tailings of uranium miners. And so it is also radioactive. And so we could go on and on and on about how pollutants get into the soil. So which is better, rainwater or well water? Well, the short answer is it depends. It depends on the history of where the water comes from.
You're listening to Science Fantastic.
Welcome back to Science Fantastic with Professor Michio Kaku. Once again, the lines are open in this hour. This is the chance when you can get to the phones and get on national radio. The number to call is 866-323-2129. Once again, 866-323-2129 is the number to call, and perhaps you can get on national radio. And once again, no question is, quote, too dumb or too stupid to get on national radio, because if you have a question about science, chances are hundreds of other people have that identical same question, but they are too embarrassed to admit it. Well, there's no reason why you can't get to the phones, therefore, and call 866-323-2129. All we ask of you is that you leave your name, the call letters of the radio station, and the city you're calling from, and perhaps you can get on Science Fantastic. Okay, well, moving right along, let's take the next listener phone call.
Hi, I'm calling from radio station 1340 in Charleston, South Carolina. And my question is, what do you know about ether as a connecting particle or substance in the universe?
Okay, well, you ask a very interesting question, which goes to the early history of relativity and light. We knew for many a year that light is a wave. It has all the wave properties that are associated with things like sound waves. Light waves can be reflected, they can be refracted, they can be interfered. So light is a wave. But light can go through a vacuum. If I get a tube and suck out all the air, light goes right through the tube. And then you ask a question which has bedeviled scientists for years. What is waving? If light is a wave and light can go through nothing, then what is waving? Well, this was really embarrassing for scientists, especially around the year 1900, when experiments were done with very fine accuracy concerning the nature of light. So the answer back then, if you read a textbook in 1900, they would say there's something called ether. Ether is a very ephemeral substance which fills up the entire universe, and its sole property is really to act as a medium for light. So if light is a wave, what is waving? Ether. Even if light goes through a vacuum, what's inside the vacuum? Ether. Ether is so ephemeral that you can't measure its properties. It appears like to be a vacuum, but it's actually not. It's full of ether. Well, along comes Einstein, who says not so fast. It's not necessary to have ether at all. And, in fact, in Einstein's general theory of relativity, the hint is that light is really a wave. And what is waving? Space and time itself are waving. In this hour on Science Fantastic, this hour is your hour. This is the time when you can shine. Well, before the break, we had a call, and it was the nature of the ether. Once again, there is a theory, there used to be a theory called ether around 1900, and ether is a substance which vibrates when light vibrates. Well, light can go through a vacuum, and so then what is vibrating inside the vacuum? Along comes Einstein, who says, you don't need the vacuum at all. You see, light can go through a vacuum, and light is basically made out of particles called photons, individual little particles called photons. And Einstein proposed what is called the photoelectric effect, where you can actually measure the particulate nature of light in an experiment. It was amazing that you could do something like that. And so we think, therefore, that light is really a particle. Therefore, you don't really need to have ether as a substance anymore. And that's why we have a new theory of light. However, I should also point out that then the question is, where does the photon come from? There is a theory that says the photon comes from a vibration from the fifth dimension. We don't have time to get into this, but if you take Einstein's equations, rewrite them in five-dimensional form, let them vibrate, what do you find? Light, photons coming out of Einstein's equations. Okay, moving right along now, let's take the next listener phone call.
Yeah, hi, I'm calling from Missouri, Lake of the Ozarks. I listen to KRMS 1150 AM. Name is Jim K. And what I'm wondering about is, why are all the planets round? If these are created by just blobs of stuff in space, how come they're also round, especially the Earth? That's really been puzzling me for many years, so I hope the professor can answer that question. Thank you.
Right. Well, even children ask that question. They say, Mommy, Daddy, the sun, the planets, everything is round in space. Why not square? Why not triangular? Well, it turns out that for small objects like asteroids, they're not round at all. And so why is that? It has to do with gravity. And as we teach our students, when we teach them astronomy, we learn that, quote, gravity sucks. That's how we teach about gravity. Gravity is attractive. But you see, gravity attracts evenly. And so if you have rock at a certain distance, the force of gravity is the same at that distance. That's why when rock coalesces to form asteroids and then form larger objects like planets, they become round because gravity begins to crush the rock spherically symmetrically. Now, when these rocks are very small in size, there's not enough gravity to make it round, so you get an asteroid. Asteroid looks like potatoes. We've photographed many asteroids now. They all look like potatoes because gravity is not strong enough to reform them in spherical shape. Now, you realize that once upon a time, the Earth was not round. About 4.1 billion years ago, an object about the size of Mars plowed into the Earth, blew out the moon. This is where the moon comes from. All the evidence points to the fact that the moon was blown out of the Earth around 4.1 billion years ago. And what did the Earth look like? The Earth looked like Pac-Man. There was a gigantic chunk of the Earth which was blown into outer space, and both fragments coalesced into spheres. That's why the moon is round, and that's why the Earth is round. So starting with Pac-Man, gravity attracts. And because gravity attracts evenly, then the gouge left by this asteroid began to fill up slowly. Cave-ins took place as more and more rock collapsed to fill in the gap created by the blowing out of the moon. And so even when something is not round, if it's big enough, it'll become round because of gravity. And so we have gravity as being one of the great forces of the universe. That's why, by the way, the rings of Saturn exist. An object that gets too close to the gravity of Saturn does the opposite. Gravity rips the moon apart. And when the moon got too close to Saturn, Saturn's gravity was so large that it literally ripped the planet apart. And that's why Saturn has rings. Okay, well, moving right along, let's take the next listener phone call.
This is Jack Condry, Charleston, South Carolina, listening to 1340 AM. I was wondering concerning greenhouse gases and the concern with global warming, why we can't use wind energy or solar energy to separate water into oxygen and hydrogen and then recombine them, burn the oxygen and hydrogen, and produce steam and then electricity. Why is this not being done? It seems too obvious. Then there's no carbon footprint. You're using water as an energy source and recyclable. Could you please comment on that? Thank you.
Well, in principle, your idea could work. Any source of energy, wind power, solar power, fossil fuels, coal, can create electricity. Electricity, in turn, when it hits water, can electrolyze the water into hydrogen and oxygen, separating them out. And then hydrogen can be used as a fuel. You can ship hydrogen to different places and burn it in what is called a fuel cell. So why don't we do that? It's a technical engineering problem as well as a mass production problem. It's expensive, that's why. We have this huge infrastructure, very streamlined, perfected over decades, that takes gasoline, burns it, and you can do all sorts of things with it. That's because of mass production, decades and decades of research. We have not yet done that much research in fuel cells. The burning of hydrogen and oxygen, which you correctly point out would be the natural byproduct of this, creates water as a waste product and energy. But the problem is we don't have fuel cells cheap enough to put in people's backyard. So the question you're asking is, yes, we could do it. In fact, high school kids can probably do it for a science fair project. It's just a question of mass production, marketing, and driving down the cost. A fuel cell car, for example, costs in excess of $100,000, and that's not competitive with a gasoline-fired car. However, Toyota and other companies are now beginning to market hydrogen fuel cell cars. We just now have to mass produce hydrogen tanks and hydrogen fueling stations. This is Science Fantastic.
You're listening to Science Fantastic. Now, Science Fantastic with Professor Michio Kaku.
This is Science Fantastic with Professor Michio Kaku. On Science Fantastic, we profile the amazing, jaw-dropping scientific discoveries that are revolutionizing our world and touching our lives. And this hour, we're going to bring on a professor of physics and astronomy at Yale University, author of a new book, Mapping the Heavens, talking about some of the deepest paradoxes in the entire universe. We're going to be talking about dark matter, black holes, gravitational lensing, all the stuff that's been hitting the headlines recently. You know, when I was a grad student, years ago in theoretical physics, it was so simple. I mean, we had atoms, of course. That's what the universe is made of. The universe is expanding. We had the Big Bang Theory, but the universe was slowly settling down. And black holes, that was like unicorns. Nope, no such thing as black holes. That's the way it was when I was a grad student. Boy, were we wrong. We had everything wrong. Now we realize that, yes, black holes are not unicorns at all. We see them everywhere we look at the center of galaxies, including our own galaxies. And the universe is made out of atoms? We now realize that every high school textbook is wrong on that question. The universe is made out of dark matter, invisible matter that is 10 times more plentiful than ordinary matter. And the Big Bang, is it slowing down? Nope. Not by a long shot. The universe is actually accelerating, careening out of control in its expansion, and we don't know why. We've invented something called dark energy to explain the acceleration of the expansion of the universe. But to be quite frankly, we are clueless. That's right. We physicists are clueless in terms of understanding what dark matter and dark energy are. So with us today to help us sort through all these bizarre theories about the universe is Dr. Priyam Natarajan. Natarajan hails from India, where she got her PhD here in the United States. She's now a professor of astronomy and physics at Yale University and is an expert on dark matter and dark energy. And so stay tuned, because after the break, we're going to enter the world of cosmology, enter the world of Einstein, as we take a short commercial break. This hour, we're going to probe some of the deepest mysteries of space and time. With us today is the author of an exciting new book called Mapping the Heavens, the radical scientific ideas that reveal the cosmos. We're very privileged to have with us Dr. Priyambada Natarajan. She's a professor of astronomy and physics at Yale University and author of this new book, Mapping the Heavens. So in this hour, we're going to be talking about dark matter. We'll talk about black holes, the Big Bang, dark matter halos, and all the mysteries that still face us as we try to figure out how to put this glorious universe together. So, Priyam, glad you could be on Science Fantastic.
Thank you very much. I am absolutely delighted to be on the program, much more so because, Michio, I've been a great fan of yours from childhood, so it's a real honor.
Okay. Well, let's talk about that. When you were growing up, what was it that got you interested in science in general, and then specifically something as rarefied as physics and astronomy?
So I grew up in India, in New Delhi, and I was always sort of a curious child. And then I guess it all really got started because I got a telescope as a present for a birthday when I was quite young, and looked through and was smitten by the night sky. And, you know, and these were days when the Delhi skies were not so polluted, so you could actually stargaze from within the city. And then I also got my first taste of research by sort of writing up a program for mapping the sky at night to see what planets would be visible above the sky at Delhi. I had, you know, a little computer quite early on. I'd learned to code. And the director of Nehru Planetarium, she got me started on my first research project. And, of course, I was reading like crazy. I was reading your books. I read Carl Sagan. I watched Cosmos. And I also had the Encyclopedia Britannica that I was sort of obsessed with, especially the maps of the sky, and, of course, maps of the land as well.
So your book is called Mapping the Heavens. So I guess that was an offshoot of some of your childhood endeavors then, right?
That's right. And, you know, in the book, I use mapping both literally and metaphorically because I like to think of maps as encapsulating our current understanding and state of knowledge, and that as our knowledge improves, I think that's reflected in how well we can map something in the sky and how we actually procure that mapping, how you actually produce those maps.
Okay. Now let's talk about the fact that you're a woman in a very rarefied field, physics and astronomy. And historically, women have had bad experiences. For example, Sophie Germain in the 1700s, way back then in France, during the French Revolution, in fact, she had to impersonate a man. She had to publish scientific papers on Fermat's last theorem as a male in order to get published, and mathematicians were later shocked when they found out that she was actually a woman and not a man. But what are your experiences 200 years after that?
Well, fortunately, 200 years, there's been a lot of progress. So if you see my photographs, you will see that I do not have to pose as a man at all. I think even compared to, say, Vera Rubin, who in the 1970s discovered dark matter from empirical data of galaxy rotation curves, she faced a lot of pushback. I think I've been very fortunate because now whatever obstacles one faces, they're really sort of subtle things that arise from sort of unconscious biases that are by now fairly well documented. I think for me the larger adjustment was, this combination of being an Indian woman scientist. So this idea of, being between cultures. So when I grew up in India, I came very young for my undergraduate to MIT in America. So that was a cultural adjustment. And then I went to England for my PhD in Cambridge, and so that was another cultural adjustment. And so in a way, I think the angst for me was more of feeling like an insider and an outsider. So it was sort of the compounding of being a woman and being sort of culturally slightly different. So it's been very interesting, I have to say. And I've been very lucky that I've had great mentors who've had enormous faith in my talents and abilities from a young age. And so I've been, as I said, very lucky.
Okay. Now let's jump right into the whole concept of mapping the heavens, the title of your latest book. Let's go back to 1920. In 1920, things were so simple. I mean, the Milky Way galaxy was everything there is. That was the universe. You could actually point and see, oh, yes, so many stars in the entire universe. Then along comes Edwin Hubble. So tell us a little bit about what did Edwin Hubble do that changed everything?
Yeah, so before Edwin Hubble came along, right, the universe was not only sort of filled with these objects that were called nebulae, but it was never clear whether these nebulae all belonged to one galaxy, our galaxy, or if they were external. So the first thing that Hubble did was basically from the size and estimation, a revised estimation of the size of the Milky Way and the Andromeda galaxy, which is our nearby neighbor, established that Andromeda was actually an external galaxy. So he actually burst open the idea that there were galaxies beyond our own that were part of the universe. But, this was not the only thing that he shook, right? At this point, the universe was also believed to be stagnant and still. And what Hubble found with data of the motions of stars in these nebulae, he found that these nebulae appear to be moving away from us faster the further away they were from us. So he kind of, in a way, unhitched the universe, right? He set it adrift. And this must have been extremely radical and disorienting at the time, because you had this very neat picture of a very quiet cosmos, which was stable. And then he not only expanded the extent of the cosmos by showing that these nebulae were distinct other galaxies, but he also set everything adrift. So it must have been very exciting and also troubling, sort of the implications.
Okay, now, if the universe is expanding and then you run the videotape backwards, is therefore a logical conclusion that maybe there was an explosion that set everything into motion. Now, that was even more radical, right? The reaction of the scientific community must have been horrendous to that idea.
Absolutely. And in fact, it was a man of the cloth, Georges Lemaitre, who actually came up with this very argument that if you run the tape backward, then it points to the fact that the universe must have had a very compact and dense start. And this was even more uncomfortable because, it really brought into the mix questions, the very questions about the origin, sort of the starting point for our universe, which were very problematic. If you wanted some kind of agency, some agent, a divine origin for the universe, then this was a very problematic start.
Okay, now let's run the videotape forward a bit. So we now have an expanding universe. And now let's say a few things about the actual Big Bang Theory itself. Who are some of the people that talked about the Big Bang? And maybe there's an echo. Maybe there's a remnant of the Big Bang that can still be measured today. So tell us a little bit about George Gamow and how some of the early scientists actually began to investigate this explosion.
Yeah, so George Gamow and two of his collaborators, Herman Alpher, they actually came up with the original sort of detailed calculations of what the energetics would be for the early start to the universe, this kind of explosive, dense, hot beginning. And they calculated how the photons, light that escaped at those early times, how it would actually get stretched out as the universe expanded, and how it would interact with the matter that was assembling into galaxies, and what kind of imprint it would leave on the radiation that was potentially detectable even today. So some of the early calculations were done by them, but, they were nuclear physicists by training, and so their work did not receive as much attention. And the first kind of comprehensive calculation was probably done by Jim Peebles, where he was able to put together this understanding of the growing formation and evolution of galaxies and structure in the universe, and the interaction of the radiation, this relic radiation that left the remnant hiss of the Big Bang, how it interacted with all this matter that was assembling and forming the tidy structures that we now see in the night sky. And what he was able to predict and calculate was that while this radiation would be uniform or on the sky, there would be very small variations in the temperature of this radiation in the sort of fifth decimal place. So very, very tiny, but there was a lot of information in those very small fluctuations, because these fluctuations carried a record, if you will, of all the structure that was encountered, so the galaxies that were assembling, that were encountered on the way. So what is really neat is the fact that one can reverse engineer and actually test ideas and theories of the formation of structure in the universe by just looking at the statistical properties of this radiation that we detect today, and was first detected by the COBE satellite, and that was launched in 1986.
Now, personally, I think it is absolutely scandalous that George Gamow never won the Nobel Prize and his students never won the Nobel Prize for predicting the basic features of this background echo that still fills up the universe. And by the way, for those people in the audience, if you want to actually detect this radiation with your television set, get an old TV set and set it between stations so you get that snow, that static on the screen. And a few percent of the radiation that your TV set picks up actually comes from the Big Bang. So you're actually intercepting some of the radiation from creation itself, which is pretty amazing. So tell us a little bit about the COBE satellite now. So you mentioned the satellite gets up there, and it actually can pick up echoes from the Big Bang. So can you explain a little bit about the COBE satellite?
Yeah, sure. So the COBE satellite, basically what the satellite contained was an instrument that could measure the difference in temperature across 2 points on the sky. So very, very sensitive thermometer, if you will. But a thermometer, because this radiation is in the microwave, is actually something that can measure in the microwaves. And you need to be above the Earth's atmosphere so that you don't have all the confounding effects of the turbulence and the effects, additional effects that would sully the data. So you needed to launch this out into space. And the COBE satellite, before the COBE satellite, people had done balloon experiments. So they would send out a balloon. It would go and make measurements of the temperature difference across 2 points. But it gave you a very limited range of experimental data. So what COBE really did was completely revolutionize our understanding, because of the kinds of measurements that it could make of all sky. So it could make an all-sky map of the microwave background radiation and the fluctuations in it. And as I said earlier, the fluctuations in it are extremely rich. They contain a lot of astrophysical information, both about the early universe and the evolving universe. So the prediction, the theoretical prediction, is that the entire universe basically behaves like what is called a black body, which it has a very characteristic distribution of energy. And it turns out that when Kobe made the measurements of the microwave background, it fit the theoretical expectations so well, and the errors were so tiny. I remember listening to George Smoot, one of the PIs of the experiment, give a talk at MIT when I was an undergraduate in the early 1990s. The error bars on the shape, the recovered black body shape measured, were so tiny that you couldn't print them on the paper thickness. They were that small. And this is spectacular. Nothing like this kind of precise work had ever been done in terms of measurements in astronomy. It really moved astronomy away from a sort of a rather hand-wavy kind of order of magnitude, not very precise measurements kind of field to one into cosmology. It basically turned cosmology into sort of a precision game.
Okay, well, let's take a short commercial break. And after the break, we're going to talk about some of the deepest mysteries of the universe, dark matter. What is the universe made of anyway? You'll be surprised to know that every high school textbook on the planet Earth is wrong in saying that the universe is mainly made out of atoms. The universe is not mainly made out of atoms. But then what is dark matter? What is dark energy? And what about gravitational lensing, by which we can prove many of these outlandish ideas? Well, stick with us.
This is Science Fantastic. Here's Professor Michio Kaku.
Welcome back to Science Fantastic with Professor Michio Kaku. In this hour, we're talking about some of the deepest secrets of the universe. Dark matter, dark energy, gravitational lensing, gravitational waves. These are some of the stuffs of the headlines that is rocking the world of astronomy. And with us today, to give us a guided tour of all of this, is a professor of physics and astronomy at Yale University, author of the book Mapping the Heavens, the Radical Scientific Ideas that Reveal the Cosmos. With us today is Dr. Priyam Natarajan from Yale University. Well, Priyam, where we last left off, we were talking about the Big Bang. However, there's a new game in town called dark matter. So first of all, everyone in our mind has an idea of what a galaxy looks like. We have this gigantic spiral of stars. It contains about 100 billion stars, for example, in the Milky Way galaxy. But now science is telling us that that's not really what's happening with the galaxy. So tell us a little bit about our new understanding of what holds the Milky Way galaxy together.
Right. So it turns out that the galaxy has much more than what you can see in terms of the stars as its constituent. So if you look at the speeds of stars in the Milky Way galaxy, you measure the speeds and you figure out what the corresponding gravitational force is that would give you the kind of speeds that you see, you find that the stars are whizzing around much faster, pointing to the existence of a lot more gravitating mass than you can see. So a simple analogy with a solar system would actually really help in understanding why this is so peculiar. So if you actually map the speed of the planets around the sun in our solar system, you find that Mercury is moving fastest. It's closest to the sun, and as you go further out, they become the other planets are moving much more slowly, and that is because the sun is the most massive gravitating body in our solar system. It dominates the gravitational force, and it's at the center. Now, if you think of a galaxy the same way, and you think of the stars, the distribution of stars, if all the matter in the galaxy is really what you see, is what you see in the stars, then the stars are concentrated in the center. So you would expect the stars stars in the innermost regions to be moving the fastest, and then it's slowing down as you go further out. In fact, the exact opposite happens in a galaxy. The stars that are further out are whizzing faster and faster, and at some point they all kind of tank and they travel at roughly the same speed. So what this suggests is that the majority of gravitating matter in a galaxy like our own is not concentrated in the center, but is extended and is somehow distributed all the way out, almost beyond where we can see the stars that belong to the galaxy. So in the 1970s, Vera Rubin and Kent Ford actually made this discovery by looking at several nearby spiral galaxies, and this seemed to be the pattern. And they suggested that the existence of dark matter, matter that is not visible, that is not emitting any radiation, and isn't part of the stellar inventory that exists in galaxies. And it turns out that the speed suggests that it has to be a very extended distribution, so rather like a dark matter halo. And subsequently, it was found that it was not just spirals, but in fact, pretty much every galaxy in our universe has this structure. So there's a lot of dark matter that's lumped in the center, and there's dark matter that is smeared all the way to the outskirts, well beyond where we see the light.
So we have this incorrect picture of a galaxy. Well, we'll talk about the correct picture after the break. Let's take a short commercial break, and after that we're going to continue a discussion of dark matter, dark energy, the creation of the universe, gravitational waves, and gravitational lensing. With us today to explain all of this is Dr. Priyam Natarajan, author of the book Mapping the Heavens. She's a professor of physics and astronomy at Yale University. And if you want to be part of the fun, why don't you give us a call? You can get on Science Fantastic yourself. The number to call is 866-323-2129. All we ask is that you leave your name, call letters of the radio station, and the city you're calling from, and perhaps you could be heard on over 100 radio stations that carry Science Fantastic. So stay tuned as we continue a discussion of the dark universe.
You're listening to Science Fantastic with Professor Michio Kaku. For more information on this and other great talk programs, go to talkradionetwork.com.
You wouldn't dare build a house without a blueprint, and neither should you invest without a plan. Hi, Sam Sorbo here. My good friends at Landmark Capital specialize in tailor-made portfolios called Your Financial Blueprint. Let Landmark Capital show you how to control your retirement and safeguard your money from government seizure, protect it from an upcoming recession, and maximize your financial growth in case of inflation. Landmark Capital can show you how to put physical metals, gold and silver, into your IRA or 401k and take physical possession today. Your 401k IRA is a ticking time bomb. The government's racked up our debt to $18 trillion, and there's currently $18.2 trillion in retirement. 12 different countries have already seized their citizens' assets like bank and retirement accounts, and it can happen here any day now, according to the Federal Reserve. Get the facts. Call 855-747-5947, 855-747-5947, or find them at landmarkgold.com. Call 855-747-5947 or visit landmarkgold.com.
Do you or a loved one suffer migraine headaches? Listen to what scientist Kurt Hendricks has to say.
If you are one of the millions of people who get migraines, you need to know about MiGrelief. Hi, I'm Kurt Hendricks, the scientist who created MiGrelief, the patented dietary supplement that addresses nutritional deficiencies in adults and children with migraines. Thousands of physicians and pharmacists recommend MiGrelief.
Call 800-MIG-7354 or visit MIG911.com.
Having a place to go after school will make you a better student. Having an outlet to express yourself will make you a better artist. Having something to do together will make you a better family. At the Y, we're helping build better friends, listeners, writers, swimmers, scientists, and musicians, one chance at a time. Get the gift of opportunity. Donate to the Y at ymca.net/give. The Y, for a better us.
Hello, I'm Roy Masters. In spite of the fact I dislike asking for financial support for my listeners, I realize the consequence of failing to do so. I will have denied my listeners the second chance to express the grace of paying forward the benefits they received through my radio program and the Foundation of Human Understanding, the organization I founded over 50 years ago. Your support will make a vital difference with a pledge as little as 63 cents a day throughout this year. Consider a donation of $19.95 per month or whatever you can afford, and help me help others, especially our returning heroes. So for the sake of the military and millions of broken lives, if you haven't done so already, pay it forward, the benefits which you've received throughout the years from one crying in the wilderness. Go to FHU.com/donate, FHU.com/donate. Thank you from the bottom of my heart.
The Foundation of Human Understanding is a 501c3 church.
You're listening to Science Fantastic.
Welcome back to Science Fantastic with Professor Michio Kaku. In this hour, we're talking about the dark universe. We're talking about dark matter, dark energy, and the fact that every single high school textbook on the planet Earth has to be rewritten. Every high school textbook says the universe is mainly made out of atoms. Wrong. That was the old picture, the picture that I learned when I was a grad student learning about particle physics and Einstein and stuff like that. And now we realize that most of the universe is invisible. So, with us today to talk about all these things is Dr. Priyam Natarajan, author of the book Mapping the Heavens. Well, where we last left off, we were talking about the fact that surrounding the Milky Way galaxy, there's a halo, a gigantic invisible halo that keeps the galaxy from flying apart. Some people say, well, so what? Let's say dark matter doesn't exist. Well, if dark matter didn't exist, the Milky Way would have been unstable and would have been flung apart billions of years ago, and we probably would not be here today. Now, how do we prove it? I mean, it's invisible, right? How can you prove the existence of something that's invisible? So, Priyam, tell us a little bit about gravitational lensing and how it is possible to get maps of dark matter.
Right. So the existence of dark matter, I think the most concrete and possibly incontrovertible evidence is from the phenomenon of gravitational lensing. So just as matter causes, the gravitational force of matter affects the motions of bodies in their vicinity, as we just discussed about the motions of stars, the other thing that the presence of mass does in the universe is alter the path of light rays. So the presence of mass in the universe can really be thought, thanks to Einstein, of as causing undulations in the fabric of space-time. So the universe is this sort of four-dimensional fabric, and the presence of mass in this fabric causes these little bumps and wiggles in the fabric of space-time. So because there's nothing above space-time, nothing below space-time, light is confined to travel on this fabric, and it traverses all the bumps and wiggles. So if you have galaxies, distant galaxies which are emitting light, the light that comes to us traverses through the bumpy fabric of space-time, and it gets deflected multiply. Every time there's mass, it gets deflected a little bit from a straight line path. And the result is that when we look out at the night sky, these distant galaxies no longer have the original shapes that they are born with. What we end up seeing are deformed shapes for those galaxies. And these deformations are due to the light getting deflected due to the presence of a lot of matter. So one of the objects that I actually work on is called a cluster of galaxies. So this is about 1,000 galaxies that are held together by the enormous gravity of a huge amount of dark matter. So dark matter in the universe is lumped very dramatically in some places, and it is lightly smeared pretty much everywhere in the universe. So clusters of galaxies, these largest repositories of dark matter, cause the most dramatic gravitational lensing or the bending of light. So you end up seeing these very distorted shapes for distant galaxies. And because we know where those galaxies are from the fingerprint, which is their spectrum, we know exactly where the galaxy is, we know where the cluster is, we can work out the amount of matter that you need to cause the deflections that we see. And it turns out you need about 10 times more matter than what you see in visible stuff in clusters of galaxies. And the same is true for individual galaxies. Some individual galaxies, if things line up just right, can also cause dramatic lensing. And these are all seen by the Hubble Space Telescope. We have these exquisite images of distorted background galaxies that are seen. And once again, when we compute the amount, the gravity of the mass...
we have to take a short commercial break.
Sure.
But after the break, we're going to continue a discussion of gravitational lensing, gravity waves, and, if we have time, even string theory. So once again, you are listening to Science Fantastic with Professor Michio Kaku. With us today is Dr. Priyam Natarajan, author of an exciting new book called Mapping the Heavens, the radical scientific ideas that reveal the cosmos.
You're listening to Science Fantastic.
Welcome back to Science Fantastic with Professor Michio Kaku. Once again, with us today is a professor of physics and astronomy at Yale University. When we last left off, we were talking about gravitational lensing. Now, think of glass. Glass is invisible, of course. Everybody knows that. But if glass is invisible, then how do you know it's there? Well, glass is there because it bends light. It distorts light, creates all sorts of false images and distorted images. That's how you know that glass is present. And the same thing can be said about dark matter in outer space. It warps light so you can see the distortions, the false images that we see with ordinary lenses on the planet Earth. So, Priyam, if it's really true that dark matter is sort of like a gigantic lens in outer space, it means that there must be false images, that you should be able to see not just one galaxy, but copies of the galaxy, just like we see distortions in ordinary glass on the planet Earth, right? Do we see these distortions out there?
Absolutely. You see multiple images, sometimes 5, sometimes 7, sometimes 3 of the same object. And we know it is the same object because we actually know we can measure the spectrum, the fingerprint of these objects, and we see that they're identical for these copies. And it turns out, recently quite an exciting discovery was that of multiple copies of a supernova that went off in the background. So you saw the light of the supernova that was lensed, and we saw multiple copies of the supernova.
Okay, now here is the big question, and that is, what is the universe made of anyway? If dark matter is invisible, it's very hard to test in the laboratory because we don't have any dark matter in the laboratory. So what are some of the leading theories as to what dark matter is?
Right, so the one thing we are very sure of is that whatever this dark matter might be made of, it is not ordinary atoms. So it's not the stuff that you and I are made of or anything that's on the periodic table. So it's sort of some exotic particle that likely was produced at vast amounts in the early universe. So, I mean, there are, of course, many, many theoretical possibilities. But in terms of particular particles, there are sort of two classes of particles, the neutralino and axions, which are very, very promising because our standard particle physics theories suggest pathways for how you could actually make them in the requisite amount to account for all the unseen dark matter in the universe, to explain all the other observational data. But, attempts to find these particles have been very frustrating, and there's been no direct detection either, or even sort of an indirect detection at CERN yet.
Okay, now we live in a wind of dark matter. The Earth, of course, goes around the sun goes around the galaxy, and so we live in a wind of dark matter, but I guess dark matter is so rare. It's neutral, doesn't interact with ordinary particles in the usual way, that I guess at the present time nobody has ever had a direct measurement of dark matter on the Earth, right?
Yeah, so interestingly, as you point out, we are sort of in a wind, so there should be a seasonal variation as the Earth moves around of this dark matter wind if we detected it. So, there is one experiment called DAMA in an underground mine in Italy, which claimed to find some kind of diurnal, sort of seasonal variation of detection of a dark matter wind. But, it's controversial, but what's very exciting is very recently 5 other experiments around the world are going to attempt to replicate. So they have the same crystal, sodium iodide crystal that was used in the DAMA measurements, and they're going to try to replicate the experiment in Korea, Australia, and again in Italy as well, to see if they see the same signal. So, so while we haven't yet detected dark matter, I think, it's just some exciting things that are up and coming that may actually reveal the presence of dark matter.
Well, if I were to put money on the table as to what dark matter is, I would say it is the neutralino, in the sense that, well, truth in advertising, I work on something called string theory, and in string theory we have higher vibrations of the string. The lowest vibration would be us, you and me. We would be the lowest vibration of the string. But the next vibration would be stable. The next set of vibrations would have no electric charge, and that's exactly what dark matter is. However, there's a renegade theory that cannot be dismissed, proposed by a colleague of mine at City College, now at Fermilab. And Joe Licken has proposed the idea that maybe dark matter is ordinary matter hovering just above us in another dimension, another universe. So gravity goes between universes, but light does not. Therefore, we would not be able to see the presence of an alternate galaxy in this other universe, but it hovers right above us, so we would feel the effects of this renegade rogue galaxy, which is sitting next to us in hyperspace. But, well, what are your thoughts? You probably heard a lot of outlandish ideas concerning dark matter. What are your thoughts? If you were to put money on the table, what would you think dark matter is?
Yeah, I think, like you, I would put my money on the neutralino, partly because, it's a particle whose properties seem to be consistent with a lot of other astrophysical observations. So neutralinos would aggregate in a way and have the kind of gravity and behave in a collision-less fashion, which is what the kind of dark matter that we need to explain all astrophysical phenomena is. But, I think what is a little disturbing, though, is that we're really narrowing down the parameter space to sort of, the interaction cross-section. We expect it to not interact very much, and we don't actually know the mass. So it is this space of possibilities that we're probing with CERN and other experiments. So we're kind of narrowing that down. So I'm a little worried that we're kind of narrowing it down. But on the other hand, I am open-minded. And, who knows? It could be one of those bizarre, unexpected speculative theories that's right. But sometimes I also wonder if it's all my unmatched socks. Because when I do laundry, I'm always missing my socks. So maybe, it's something. I'm just kidding.
That's a lot of socks. Okay, well, unfortunately, we've run out of time. So, Priyam, thank you so much for being on Science Fantastic.
Thank you so much for having me. This was fun.
Okay, once again, you've been listening to Dr. Priyam Natarajan, author of the book Mapping the Heavens. So stay tuned as we continue to explore the cutting edge of science.
Now, Science Fantastic with Professor Michio Kaku.
Is Science Fantastic with Professor Michio Kaku. On Science Fantastic, we profile the amazing, jaw-dropping scientific discoveries which are revolutionizing our world and touching our lives. And in this hour, once again, we're going to throw the lines open because this hour is your hour. This is the time when you can ask that question, make that comment that you've always been wanting to ask, but never had the courage. Okay, well, without further ado, let's move right along and take the first listener phone call.
Hi, Professor Kaku. First of all, I'd like to say I'm calling from Jackson, Mississippi. I'm not sure of the radio station. And second, I would love to say that I love watching you on the Universe. I watch you on your channel all the time. But my question is, what do you actually believe gravity is? I know it's a complicated question. I know we still
Well, you asked one of the most difficult questions in the universe, and that is, what is gravity? Ironically, it was gravity that was the first force to be more or less described mathematically by Isaac Newton back in the 1600s. But there was a problem with Newton's equations. When you write down Newton's equations, you realize that gravity spreads infinitely fast throughout the universe. So if the sun were to disappear right now, if the sun were to disappear, it would affect the Earth immediately. We would be hurled into outer space instantly. Well, there's a defect there, and the defect is that there's no mention of the speed of light. We see no deviation from Einstein's theory in the laboratory, and Einstein says nothing can go faster than the speed of light. Even gravity cannot go faster than the speed of light. So Einstein had to introduce a new picture. He replaced this idea of an instantaneous force that could spread instantly throughout the universe, and we replaced it with a fabric, so that if the sun were to disappear right now, the ripples of that titanic disappearance would then permeate around the universe, just like waves on a pond emanate from the place where the stone first hits the pond. Well, now we have the quantum theory, and the quantum theory says, no, this can't be right, because forces are carried by particles. And so we have to take Einstein's theory and bust it up into little particles called gravitons. Unfortunately, gravitons have never been seen in nature. We know they must exist. And gravitons create waves. Now, we've seen those waves. These waves are called gravity waves, and they were seen just a few months ago, making headlines around the world. But these gravitons, that is the origin of these waves, little particles of gravity, have not yet been seen in the laboratory. And it may take many decades before we have instruments sensitive enough to pick up gravity waves. Now, why is that important? Because that would give us a unified field theory of everything. So the short answer to your question is, we don't really know. However, the leading theory is that these gravitons are actually tiny little vibrating strings. So think of a rubber band. A rubber band vibrates, creates all the particles of the known universe, but from a distance, the rubber band looks like a dot. That is a graviton. And that's how we introduced the quantum theory into Einstein's theory, by introducing little loops of gravity, little strings like rubber bands. And these rubber bands can vibrate at different frequencies, giving us all the material particles of the universe. Now, you may say to yourself, well, if that's the latest picture of gravity, then how come we don't win the Nobel Prize for this idea? Well, there's a catch. And the catch is that these strings cannot vibrate in ordinary 4 dimensions. They have to vibrate in 11-dimensional hyperspace. At that point, even physicists begin to roll their eyes into the heavens and say, what the hell did you just say? Well, that's what one of the predictions of string theory is, that these strings are in some sense magical. They cannot just vibrate in ordinary 4 dimensions, the dimension of Einstein, but 11-dimensional hyperspace. Now, we've seen no evidence of 11-dimensional hyperspace. However, we're looking at atom smashers around the world, especially the CERN atom smasher outside Geneva, Switzerland. We're beginning to conduct some of the first experiments looking for the presence of higher dimensions. And if these higher dimensions exist, then can parallel worlds also exist? In other words, parallel universes. They're not so far-fetched anymore. We think that perhaps in our universe, the speed of light is a constant, and we sort of know that the universe is expanding. But what about these other universes? Well, to find out more about these other universes, you may want to get a copy of my earlier book called Parallel Worlds, where I talk about the latest understanding of what is gravity. So such a simple question, why do things fall down? Such a simple question takes us into the realm of higher dimensions, parallel universe, and God knows what else. Okay, well, moving right along, let's move on and take the next listener phone call.
Hello, this is Gary in Great Falls, Montana. I don't want to be a smart aleck about anything, but I think that zero gravity is easy to understand if you think about it as the center of of everything. Zero gravity is in the center of our planet, and zero gravity is in the center of the sun, and that's what holds the solar system together, and that's why we don't want to see zero gravity in our planet, because I would imagine that temperature at zero gravity isn't too fun to be in at the center of our planet either. Anyway, that's I always was a simple-minded person, but that's kind of a simple idea for zero gravity. Anyway, thanks.
Well, you ask a very interesting question that even Isaac Newton asked himself 300 years ago, and that is, what is the gravity at the center of the Earth? Well, you see, at the center of the Earth, there's no direction because, of course, the Earth is a sphere, perfect sphere, let's say. There's no left, right, up, down, whatever. So at the center of the Earth, said Isaac Newton, gravity must be zero. Zero because of symmetry, nothing else. At the center of the sun, gravity must be zero. At the center of the Earth, gravity must be zero. But you see, that doesn't explain what happens away from the center, where, of course, most of the action takes place. We want to know what the gravity is at the Earth, at Jupiter, at the different planets. And just to say that gravity is zero at the center of the Earth doesn't explain what happens off-center. And that's where Isaac Newton's equations for gravity come in. Isaac Newton said that the gravitational force goes as 1 over r squared. So the farther you are from the center of the Earth, the weaker gravity gets, except at the very center of the Earth, where, as I mentioned, all the forces cancel out and there is zero gravity. So in other words, we need a theory not just at zero gravity, we need a theory at non-zero gravity, and that's where Isaac Newton's equations come in. And then even those equations have to be modified because they don't include the speed of light. Then we have to go to Einstein's theory, and even those theories have to be modified because they don't include Planck's constant, the constant that measures the strength of quantum forces. So you see that asking a very simple question about zero gravity immediately starts to put you into the realm of the universe itself.
You're listening to Science Fantastic with Professor Michio Kaku. Here's Professor Michio Kaku.
Welcome back to Science Fantastic with Professor Michio Kaku. The lines are open. This means that this is your hour. This is the time when you can get to the phones and call 866-323-2129. Okay, once again, moving right along now, let's take the next listener phone call.
Who were the 3 greatest women of science, and what were their theories? Eugene.
Well, you ask an interesting question because there's so many to choose from. The first on the list would, of course, be Madame Curie. Madame Curie won 2 Nobel Prizes, not just one in physics, one in chemistry. And she helped to open up the whole realm of radioactivity. Radium, for example, is one of the elements discovered by her. Polonium is another. Curium, another element, was named after her. And so she ranks up there in terms of our understanding of the nuclear force. And there's so many other scientists who are perhaps less well known, but made a significant impact on the history of science. For example, Sophie Germain. Sophie Germain lived in France at the time of the French Revolution in the 1700s, a very dangerous time to live there. But she was very much enamored of science, and especially mathematics, but she was a woman and couldn't get published or even interact with other male mathematicians. So what she did was she impersonated a male. She took on a man's name, wrote letters to all the great mathematicians of the age, and they corresponded with her because they realized, oh my God, we have a prodigy here. And only later did they find out, oops, she's a woman. And when they did find out, well, there were some people who wouldn't invite her to different award ceremony. In fact, in one ceremony, she was given an award, but she couldn't even come to receive the award because women were not allowed at that ceremony. And also another woman who suffered from discrimination was Vera Rubin. Some people think that she is up for a Nobel Prize because she was one of the first people to alert us to the existence of dark matter. It turns out that the Milky Way galaxy spins too fast for its own good. Believe it or not, the Milky Way galaxy spins so fast it should fly apart, but there it is, stable for billions of years. So here we have this gigantic spiral in outer space. You see it every night when you look in the night sky, this huge disk. But what holds this disk together? Something alien, something new called dark matter. So many people think that Vera Rubin will possibly win the Nobel Prize for pointing the direction to what is called dark matter, which we now know is 10 times more plentiful than ordinary matter. Okay, well, let's move right along and take the next listener phone call.
Yeah, hi, my name is Mark Robertson, WNDB 1150, Daytona Beach. And my question is, when I was little, I had fillings, and I could have sworn I picked up a radio station with my fillings. And I kind of heard about it, so I just want to know if that's possible. Thank you.
Well, not only is it possible, but this has been going on for many a decade. When radio was first introduced on a widespread scale back in the 1930s, people began to say that I think I can hear the radio in my teeth. And here's how it works. First of all, how is radio created? Radio is created by having electricity go up and down an antenna or a piece of metal. And so the very fact that you can have electricity go up and down a piece of metal emits waves, and these waves are radio waves. Now you can run the videotape backwards, and that is if you have a piece of metal in the presence of radio, it'll also pick up that radiation. And if it's in your teeth, it'll actually create vibrations. And these vibrations can be felt because, of course, it's in your mouth. And that's where radio waves can be picked up in your fillings. And when you're in school, of course, we can do that with crystal sets, but you can also do that with your teeth. Welcome back to Science Fantastic with Professor Michio Kaku. And this hour, once again, we're throwing the lines open, and this is where the fun begins. Okay, well, moving right along, let's take the next listener phone call.
Yeah, listening from Northeast Pennsylvania, WILK, and the sun will interest me the most. How it keeps, where the energy comes from, how it keeps shining, the diameter, and if it shines on the backside also. Thank you very much. Bye-bye.
Okay, well, you ask a question that has fascinated the ancients ever since we looked at the night sky. Well, of course, when ancient humans began to domesticate fire, they thought, aha, maybe the sun is nothing but fire in the sky. So that was the first great theory that actually made some sense. But in the 1800s, scientists began to realize that, well, fire requires oxygen. You can calculate the amount of oxygen required to set the sun on fire. And when the calculation was done, they realized, oh, my God. It turns out that the sun would have burnt out thousands of years ago. And there's no way that the sun could shine for millions to billions of years. And so we had a problem. And the problem is, what lights up the night sky? A new kind of force, a force beyond simply fire. And then along comes Einstein in 1905, who says, I think I have it. And that is E equals mc squared, meaning that even a small amount of M can create a large amount of E. A small amount of matter in the form of hydrogen can create enormous amounts of E in the form of sunlight. Then in the 1930s, Hans Bethe, who would win the Nobel Prize for this, sat down and worked out all the steps by which hydrogen fuses to create helium and basically creates all the known elements inside the sun. And so the sun is basically an oven that cooks hydrogen to create helium, then cooks helium to create lithium, and on up the periodic chart. And so we now had a mechanism by which we can calculate the amount of energy created by the sun, and it worked out perfectly. So we now realize that the sun is a hydrogen bomb, a gigantic hydrogen bomb. It doesn't blow apart completely because gravity holds it together. So the sun is, in some sense, a stable object because gravity wants to compress the sun, but the nuclear force wants to blow the sun apart. And the two forces just match each other, and so we get equilibrium, and that's why the sun is stable, giving us sunlight. It is spherical because gravity attracts spherically. Gravity attracts evenly. That's why the sun is round, for example. And it releases energy via Einstein's equation, E equals mc squared. In fact, when I was a grad student years ago at the University of California at Berkeley getting my PhD, my roommate was an astronomy grad student. And in the morning, he would make some wisecracks, and he would say, I'm going to cook a star today. I'm going to put a star in the oven. And when he came home at night, he said, well, I just took the star out of the oven. Well, I thought my roommate was nuts. I mean, how can you put a star in the oven? And then I asked him one day, and he explained to me. We know so much about the equations for sun that we can put the equations in the morning into the computer, and by night we can have a mature star. We can actually cook a star in the memory of a computer. Welcome back to Science Fantastic with Professor Michio Kaku. It's open mic in this hour, meaning that you can get to the telephone and give us a call at 866-323-2129. And why don't you become part of the fun? Instead of just listening to the radio, why not be part of the radio by giving us a call at 866-323-2129. Let's say you're just walking down the street and wondering, what does it all mean? Where does everything come from? The mountains, the sky, the oceans. Where did life come from? What's out there in outer space? Is there life out there in the universe? These questions are all fair game on Science Fantastic. Okay, well, moving right along now, let's take the next listener phone call.
Hi, my name is Frank, W-I-L-K, Wilkes-Barre, Pennsylvania. My question is that when do you anticipate when NASA would be able to put a spacecraft into space where there won't be no booster rockets, there'll just be one spacecraft itself, land like on, they say, the moon, and return to Earth, and without no extra booster rockets or just one spacecraft. Thank you very much. Have a good day. Your show is the best. Thank you.
Well, you ask an embarrassing question because scientists for the last century or so have been using chemical rockets to go into outer space. So in other words, we have to carry our fuel with us which is, if you think about it, a waste of fuel, because the fuel has to have enough fuel to carry itself into outer space. And if you think about it, most of the rocket's weight is fuel. Therefore, if you could jettison the empty canisters, you could save on the cost of the rocket, and that's why we have booster rockets. So the booster rocket would be the first stage of our rocket ship, and the last stages would be the actual payload. That's been the way it's been with rocketry for almost 100 years. But NASA is slowly catching up to the idea that maybe we should have another kind of rocket without having to use these booster rockets. However, here's where it gets rather iffy, because these alternatives to chemical rockets are not as efficient as chemical rockets, but let's review some of them. One of them is the plasma ion rocket. Instead of shooting out chemicals, it shoots out ions. That's great, but the amount of ions that you can send out is very, very thin. So we don't expect to have them anytime soon. And then we have laser rockets, and I'll say a few things about laser rockets after the break. Laser rockets have no booster rockets at all.
This is Science Fantastic. Here is Professor Michio Kaku.
Welcome back to Science Fantastic with Professor Michio Kaku. Once again, we're going to throw the lines open because this hour is your hour. Well, before the break, we had a simple question, and that is, what will replace the booster rocket? Well, it's not such an easy question because we've been wedded to chemical rockets for almost 100 years. We're playing with other kinds of rockets, like, for example, the plasma ion engine. The plasma ion engine shoots out ions instead of hot chemicals. In principle, they can operate for years at a time instead of just a few minutes, which is the case for ordinary booster rockets. The catch there is that ion engines produce very small amounts of thrust. For long periods of time, of course, like for years in principle, but the total amount of thrust is quite small, and therefore you don't get the blast of energy that you get with an ordinary chemical rocket. The next generation of rockets, perhaps beyond ion engine, is laser-fired engine. We get a sail made out of, let's say, some kind of reinforced tinfoil, and we shoot a laser beam on the foil. The foil acts like a parachute. By blasting the tinfoil with enough light energy, it'll propel it. In fact, Stephen Hawking was at a press conference just last month where he talked about sending a starship that would go not just around the Earth, but to the stars, propelled by gigantic banks of laser beams fired at a parachute containing a small payload, a small little chip, which would then go to the stars and take photographs and things like that. Well, that sounds like a great idea, right? But what's the catch? There's always a catch someplace. And the catch there is that the laser beam has to be enormous in terms of energy, 100 megawatts, 100 gigawatts of energy. That's the equivalent of 100 nuclear power plants. So think of having an array of 100 nuclear power plants blasting its energy into outer space, inflating a parachute that then hurls a small payload, a small chip, near the speed of light to a distant star. And so you can see immediately that, well, it sounds like a great idea, right? Rockets without booster rockets, but the practical details of that are pretty daunting. And we don't expect plasma rockets to go into regular use for a few more decades. And perhaps by the end of the century, we'll have enough resources to send laser payloads into outer space. Okay, well, let's move on to the next listener phone call.
Hello, my name is Peter, and given that you wrote a book about neurology, basically, I was wondering about the future of the mind and an extension of the work of Jose Delgado, who claimed in the CNN report back in the 80s, I believe it was, that he was able to affect the thought processes of monkeys with radio frequencies. There's been a lot of talk about that now. That's what I'd like to talk about. So my name is Pete. Bye.
Well, you ask an interesting question because, yes, back in the, even as far back as the 60s, scientists were experimenting with monkeys, not using radio, but actually using wires to connect them to mechanical devices. In one situation, which was photographed and recorded, a bull had electrodes placed in his brain, and then it was, in fact, connected with radio to a switch. And in one famous experiment, a Yale professor puts on the uniform of a matador and goes into the bull ring with a live bull. As the live bull starts to get aggravated and lunges at the Yale professor takes out a button, pushes the button, and stops the bull dead in its tracks. An incredible feat. But certainly possible because now we know the basic outlines of the brain. We know, for example, where in the brain you have to electrify in order to get the bull to stop. In fact, we have maps of the brain now, maps of the brain where we know that this part of the brain connects to your left hand, that part of the brain connects to your right hand, and by putting electricity in these spots, you can actually make your left hand and right hand move. In fact, the military is now backing this. We're not just talking about scientists at Yale University, but $150 million has been allocated by the United States Pentagon to create an Iron Man outfit. An Iron Man outfit controlled electronically by chips in the human brain that then allow the brain to control an exoskeleton so that paralyzed people can now walk again. And that's just one of several experiments that I mentioned in my book, The Future of the Mind. So Iron Man is not so far-fetched. And then if you connect the mind, the hippocampus of the brain, to the Internet, you can actually send memories. Memories can be sent electronically. Here's how you do it. You put 2 electrons on either side of the hippocampus located at the center of the brain, and then you train a mouse, for example, to perform a task. You record the signals that go across that part of the brain, the hippocampus. You record it like a tape recorder. Later, you play it back. You play the same impulses back into the brain of the mouse, and bingo, the mouse executes that very same feat. Well, these and many other incredible discoveries are mentioned in my book, The Future of the Mind. Well, unfortunately, we have run out of time. Once again, this is Science Fantastic as we explore the cutting edge of science.